Okay, fantastic.
Hi, tonight we have Professor Matteo Mitrano will tell us about scattering ultra-fast X-rays on quantum materials.
Thank you, Bob, for the invitation, and thank you, everyone, for being here tonight. So tonight I will tell you about recent work that condensed matter physicists are doing to understand what happens at the microscopic level when we shine light on certain materials that have peculiar or intriguing quantum properties. And in particular, I will tell you more about the experiments that we do with ultrafast X-rays. So stop me at any moment if you have questions. So let me just say that, so the premise for this talk is that over the last few years, believe it or not, there has been a substantial research activity in the study of light-induced phenomena in solids. So there has been, in particular, attention to the possibility of controlling the electronic properties, magnetic properties, topological properties of materials with interaction with strong laser pulses. And I will just show you here a small compilation of examples of interesting results that were that stem from this kind of focus. So it has been possible to, as an example, induce metastable Eden phases. So Eden phases are certain states of matter that are not present in the equilibrium phase diagram. So as an example, certain structures that are that cannot be mapped at equilibrium. So if you try to vary, as an example, the temperature, the doping, the magnetic field at equilibrium, you will find all sorts of phases in certain materials, like different crystal symmetries and so on. Metastable Eden phases are phases that can only be induced through a very specific interaction with the laser field and that have no correspondence with equilibrium phases. So this essentially means that you can build non-equilibrium phase diagrams. That is a very intriguing possibility in terms of discovery of new states of matter. There has been a variety of photo-induced phase transitions. Photo-induced phase transitions are a bit different in the sense that you have a well-known phase transition at equilibrium, as an example, insulator to metal, and you can trigger this phase transition on demand by shining a laser onto the material. And therefore, you can actually control the material at very fast time scales. And this has technological applications if you want to make a faster computer, a faster magnetic memory, and so on and so forth. And here are some examples, just for your record. It has been possible to engineer the band structure. So in principle, if you have very strong electric fields, and tonight you will see an example of this, you can actually perturb the band structure, perturb the energy levels in a material, and deform the states that electrons are allowed to move in. And this has been particularly fascinating for a number of reasons, and exploded recently with the so-called Floquet engineering that I will tell you later during the talk. It has been possible to control magnetic materials, as an example, by switching magnetic states, demagnetizing magnetic states by changing the axis of magnetization of a material. And it has been possible to switch also ferroelectric. And this is work that I personally did during my PhD to induce a superconducting state. So to induce a state with zero resistance outside of equilibrium by using a specific light excitation that is resonant with certain lattice vibrations. So you deform the structure and you obtain a better superconductor. That is a very sought after state of matter with technological applications ranging from computing to transportation, lossless power grids, and so on and so forth. Now,
so these
yes,
are all very time dependent, right? So you flash the light, then your hidden phase appears, and Then when the carriers decay, boom, it's gone again.
Well, in some cases they are metastable because you can really move into another potential, into another local minimum of the potential of the free energy. And so in some cases there is a reason, as an example, a recent experiment by Nova in Science in which they show that you can induce a ferroelectric transition that is metastable. It stays for hours.
Oh, metastables really clicks, and then you're going to have lunch and come back, and it's still there.
Yeah. So you launch it, it evolves over a femtosecond time scale, and then stays there for hours. So it really depends. In some cases, it's really fast. In some cases, it can be metastable. So it really depends on the properties and the specific microscopic properties of the system. And this is part of the fascination of the field. Like, we are trying to understand and to predict that. Thank you, Bob. So now, this is concerning the optical control. Now, the point is that why X-rays? And X-rays are actually a fantastic tool to study the microscopic dynamics. So I was telling you before the beginning of this talk that if you can use X-rays to map the position of atoms. So X-rays are essentially photons with a very small wavelength that is comparable with the distances between atoms in solids, and so you can do diffraction. And if you do time-resolved diffraction, you can actually resolve the light-induced motion of atoms in materials. And this is, as an example, the motion of atoms in a cuprate superconductor that has been excited with a strong infrared pulse. And one of my former colleagues at Max Planck made this very beautiful measurement in which he was able to measure the time-dependent behavior of certain diffraction peaks with certain indices, and to map and to reconstruct the transient structure of this material. And you can see that in this case, as Bob was mentioning, this displacement happens over a picosecond time scale. Sub-picosecond time scale, so this is a millionth of a second. So it's very, very fast. But you can actually have situations in which these dynamics persist for much longer times. But these are very crisp example. But the thing is that X-rays are not just good for doing diffraction, but actually can be used to study things beyond the structure, and you can actually study spin dynamics. It will sound counterintuitive, but actually there are circumstances in which you can study the behavior of the electronic spin in materials with photons, and you can study charge degrees of freedom, as an example, plasma oscillations and so on, at microscopic scales. So this means that you can really study short wavelength behavior that corresponds to microscopic charge and spin dynamics in solids. Now, how do we actually do it? The way we do it is by using so-called free electron lasers. So free electron lasers are quite unique instruments, and really position the science we do at the interface between condensed matter physics and high energy physics. This is an example. This is the LCLS in California, in Menlo Park. This is a 2-mile accelerator that was used to study particle collisions in the 70s, in the 80s, and
yeah.
Come again?
No, I just said it's SLAC, right?
Yeah, it's SLAC, yes. And then this LINAC, this linear accelerator, is being converted to produce X-rays with femtosecond pulse duration. So what has been done is that it has been placed an undulator that I will tell you in a second about, and this undulator converts high energy electrons, allows electrons to emit X-rays with a very, very high brilliance that are used for our experiments in these end stations, in these experimental halls. This is an instrument so big that you can really see it on Google Maps from the satellite. So I strongly encourage you to look it up on Google Maps. I find it amazing. And when you do the experiment, you are essentially the only user. There is only one user at any single time. So the entire machine is working for your experiment while you do it. Right now, there has been some multiplexing, but mostly this is not like a synchrotron in which there is 40 experiments running in parallel. This is one experiment per at each given moment of the operation. And the way an accelerator works is based on a concept that should be familiar to most of you from E&M and so from 15B and 15C. So essentially, it works on the so-called Bremsstrahlung, and essentially it's generating X-rays is done by accelerating electrons to very high energy, giga-electron volts. You have an electron bunch that then goes into an undulator. An undulator is essentially a sequence of magnets with opposite polarity that make the electron travel in this kind of serpentine into this zigzag. And this undulator is really, really long. I mean, at the LCLS, this undulator is about 170 meters long. And it's perfectly aligned within micron accuracy. So to make sure that you compensate even for the Earth's crust curvature, and you get these very, very brilliant coherent X-rays that are multiplied and saturated by these transition radiation. The thing that you're seeing here is essentially a working principle for an X-ray laser, and you get pulses that are extremely coherent, extremely brilliant, and tunable between the soft X-ray regime, so between 250 eV, so nanometer wavelengths, to sub-angstrom wavelengths. And this is how we generate the light that we use in our experiments. So the technique that I started working on and that we pioneered together with another PI in Brookhaven. So there was work done at the Brookhaven National Laboratory, and by me and my former faculty mentor in Illinois, we pioneered this technique of time-resolved resonant inelastic X-ray scattering. This is a very complicated technique, but just to give you a flavor, essentially what happens is that you take a material here. Can you see my mouse, by the way?
Yeah, it shows up.
Okay, so you take a material here, you excite it with a laser to control its properties. So this laser will be at, as an example, terahertz frequencies. And then what happens is that you probe the excited state with a delayed X-ray pulse, and you tune the delay between these two pulses. That's how you get the time-resolved snapshot. And you do a stroboscopic measurement. This X-ray probe is tuned at resonance with an energy at resonance with a certain electronic transition that brings one electron from the core to the valence. So these are really transition between 2p 3d orbitals, as an example. And then this excitation relaxes back to equilibrium, and in the relaxation, it emits another photon with a different momentum and with a different energy. And this different energy and different momentum corresponds to an energy exchange between the electromagnetic field of the X-rays and a particular excitation of the system. And you can map these things in momentum space to actually reconstruct the spectrum of the excitation of a given material. So the interesting thing of this spectroscopic method is actually gives you access to charge and spin dynamics of driven materials at finite momentum with extremely high time energy and momentum resolution. And this is pretty unique. You cannot do it with optics. Optics doesn't give you momentum because the speed of light is so big that doesn't allow you to get momentum resolution at optical frequencies. Now, what I will show you.
What sort of resolution energy resolution do you get? Because I was thinking you're starting with a really high energy, then so what's the uncertainty and
So the experiment that you will see here as being quite pioneering, and the resolution was of the order of was not fantastic. It was of the order of 600 millieV. So it was pretty poor. However,
sounds good to me. Sorry.
No, but I can tell you that the rumor is that right now there is actually a spectrometer in Hamburg that just came online, and I still have to hear the details on town hall in 2 weeks. But apparently there has been an improvement by an order of magnitude. And so we are probably below the 100 millieV energy resolution right now.
Okay. Amazing. Yeah.
Okay, so today I will tell you about two different phase transitions, two different applications of this kind of spectroscopy. So in the first one, we will follow a non-equilibrium phase transition. I decided not to go too much into the details of this phase transition and why we study it. It's actually really important to understand the behavior of superconducting materials. But essentially, what we did is that we used this technique to study a particular phenomenon that is the formation of a charge density wave in a copper oxide. So these materials are the original high temperature superconductors discovered by Bednarz and Müller in 1986, the year I was born, and
it's yours.
Yeah, it's true. And,
sorry, go ahead.
And you have the formation of so under certain conditions, you have that actually electrons do something amazing. They self-organize in a pattern, in a charge density wave. So they form a periodic wave of where there is more charge or less charge. And this wave has a period of 4.3 lattice parameters. So this is a very short wavelength, and therefore optics doesn't really resolve it, because this will give rise. I mean, it behaves like a diffraction grating, and if you put X-rays on it, it will scatter X-rays at large momentum, because this is a very short wavelength. So the momentum goes with 1 over the wavelength. So you need X-rays, and we therefore studied this phase transition with X-rays that have enough momentum to cover this momentum range. And so when I say that you can reach these peaks, I really mean that you can see these peaks with the X-rays on a detector, and that you can move your sample and your detector in a kinematically allowed angle. So because otherwise there are in some cases no angles that can bring you to see a certain reflection in a certain in a certain position in space. Now, what we see here is that we did spectroscopy of the order parameter. The order parameter for this transition is essentially this diffraction peak. This is like a grating, and so what you're seeing is that if you scan the momentum, you have essentially a very sharp feature located at 0.23 that corresponds to this periodicity, and then you have these absorptions at finite energy that corresponds to local excitations of the atoms. These are like Dirac deltas. In real space, they are localized excitations, and so they don't change in momentum. But this thing, it changes, and it forms a really sharp peak. So in our experiment here, we are moving this angle theta to scan H, and we are now doing an experiment in which we pump the material with light at 1.5 eV with a 50 femtosecond pulse duration and probe it with ultrafast X-rays. Now, this is the first weak spectrum taken on these materials ever. This was the first time this was mapped with energy resolution. And what you see is that when you pump it you start puncturing disorder in this pattern, and therefore the peak will go down. And now if you integrate the energy in between like 3-4 of these beams, so over a window of about like 1 eV, 1.5 eV, you will get actually that you will be able to see that this peak actually goes down and becomes broader. And the fact that it becomes broader is telling you that the number of carriers that contribute to this wave is decreasing, and not only it's decreasing, but is also this pattern is becoming more and more disordered. And actually, you can quantify some important things about this disorder by looking at the shape of the peak. I will not go into the details, but I will tell you something really cool. This is just a snapshot before and after the pump, but actually we have been able to do the entire movie. And so today we are in a position to make the entire movie of this excitation. And as you can see, this is essentially sitting on the top of that peak in momentum space and varying the time delay. And now we can really take snapshots and make a small movie of how the pump is actually perturbing this phase. And I will show you a phase transition as it happens. And here you will see, this is before the pump arrives. This is the reflection of the order parameter. The pump comes, this reflection goes down, and then it takes time to come back. And you can measure, you can really stay there with a stopwatch and measure how much time does it take for this order to form again. And I will speed it up here. And you can see that it goes back to equilibrium very slowly. Actually, there is a specific law that tells you how slow this thing will go. And it has to do with the presence of defects in the pattern. But the important thing is that you can really see that at equilibrium, you have a very strong order parameter. The pump comes, and then it will go down. And it's depleted. And you can really see the physics of these electrons that are moving as it happens. And this was in our view a breakthrough, because you can really do movies in the X-rays. It's like having an X-ray camera. Okay. Now, what I wanted to tell you is that in principle, this is very, very interesting and allows you to study photo-induced phenomena in quantum materials. And I will tell you that actually not only you can take snapshots of these phase transitions, but actually you can interrogate materials and measure how light contributes to the change of electronic interactions. I will try to make it as simple as possible here, but essentially the basic idea is that in many of the materials that we study, there is a subtle competition between delocalization and localization. So electrons can move around, and we quantify the energy associated with this kinetic motion of the electrons in the lattice with a parameter that is called T, not to be confused with time. That is an hopping energy. But when you put two electrons on top of each other on a single site, they will repel each other. This is the Pauli exclusion principle. You will have to pay a price. It's Coulombic. It's due to the Coulombic repulsion of these two electrons that are close together. And what happens is that these electrons, you will pay a price to put two electrons together on the same site. This price, this Coulomb energy, is quantified by a parameter called U. I will not tell you all the details of this, but at the most basic level, this is encapsulated by a so-called Hamiltonian operator in which these two phenomena are corresponding to two different terms with different signs. So they are competing with each other. And there is this subtle balance that gives you the emergence of different phases in many materials. Now, what I will show you is that you can use light to change the balance, to tip the balance of these phases. And we can measure transient electronic interactions by using the same scattering processes that I told you at the very beginning. But this time we don't care about this photon, this last photon. We just focus on the absorption part. And I will tell you that we can actually get quantitative information just by looking at the absorption spectrum of the X-rays, and by looking at how much light is absorbed by the material. So in this material, I'm studying always LBCO, that is always this cuprate that you've seen at the beginning. Essentially, you have copper-oxygen planes in which you find copper orbitals, oxygen orbitals, and they form also a hybrid state that is the so-called Young-Rice singlet. If you look at the bands, at the very basic level, what you have is that the coppers contribute 2 bands that split because of this energy cost of putting 2 electrons next to each other. And then you have the oxygen P bands that are in the middle. And here you have this hybrid band that is located between the oxygen band and the copper band. So this is well known. What we do is that we want to see whether we can change the position, the energy of these bands. And we study, therefore, these transitions. We excite core electrons and we send them into these unoccupied states. And we see what happens if you illuminate the material. So at equilibrium, these transitions are well visible. So you have that when you sit on top of the oxygen absorption, you see these 2 features that are very well defined in the pre-edge region. I will not comment on this shaded area, but trust me, this is the main edge. It doesn't really carry that much information as these 2 pre-peaks. And then there is this prominent peak here that is essentially the same little peak that you see here, but it's due to the copper band. So here on the copper is more evident. So these are photons at different energies. So here we are at 500 eV, here at 900 eV. And these are really different atomic resonances. So these are 1s to 2p transitions of oxygen. These are 2p to 3d transitions in copper. And what we do is that now we study the behavior of these peaks, 1, 2, 3, okay? And this is at equilibrium without any light. This is what happens before the pump. And this is what happens after the pump. So we zap the material with a strong laser field. And we find that this peak goes down a bit, broadens, but actually doesn't really care about the pump in the sense that it doesn't really move. This peak actually moves by about 63 millieV. It seems really a small number, but actually is a big number. I can tell you that is a fairly big number. And this peak moves by under 25 millieV. You can really see it by eye that it's moving. And this is telling you that something is going on. And the band structure is changing due to the pump pulse. This phenomenon is really, really quick. So you really need very fast pulses in order to see what's going on. So this is the time scale of this phenomenon. So everything is gone within 1 picosecond. So this phenomenon is really quick, happens. These are high energy phenomena. And when you sit on top of this band, actually the electrons decay is lower than when you sit on top of this band. I will not go into the details, but essentially the argument is that these correlated carriers need to dissipate lots of energy, and that is really unlikely to happen within a single scattering event. I will not go into the details of this, but I will tell you what is that we are learning from that. So I told you that the band structure is changing. So what we did is that we did some theoretical simulation with a small minimal model. And we did a calculation that is so-called exact diagonalization, in which we build a matrix of the orbitals, we diagonalize, and we calculate the states for a small ensemble of atoms. And what we observe is that the only scenario compatible with our experimental finding is that we are actually changing the cost that the energy cost of putting 2 electrons on the copper orbital. So any other parameter involved in this physics, in the physics of this material, will give you a shift that is not compatible with the data. So if you change the kinetic energy, if you change the Coulomb repulsion on the oxygen sides, it will not change the spectra as we see. And if we now follow the dependence by systematically tuning this parameter, we are actually able to tell you how much this parameter is changing. So based on the spectral features, I can tell you that the energy cost that it takes to put 2 electrons on the same site in copper is reduced by 140 millieV. 140 millieV doesn't seem a lot, but is actually a pretty high energy scale. So we are talking about something of the order of more than 1,000 Kelvin. Okay, so this is a very high temperature. And now, what is going on at the microscopic level? At the microscopic level, we didn't really pin down exactly the mechanism, but there is 2 very strong indications of what there are two mechanisms that could be at play, and I'm almost done. The first mechanism is that this pulse is actually exciting carriers, and these exciting carriers form a polarization cloud around the copper site that screens the charge and reduces the effective energy cost of putting 2 electrons in the copper orbital. So this is a screening enhancement in more technical terms. And this is being calculated by some colleagues with other theoretical methods. And it has been estimated to be more or less of the same order of magnitude. A second possibility is that we are actually dressing the orbital with a double occupation with the virtual states that are addressed by the electromagnetic vector potential. And we are actually by summing up all the series of states that you can have in this parametric process at overlap with the pump, you can actually reduce the amount of energy that it costs to put 2 electrons on the same orbital state. And this could also lead to this kind of shift of the density of states. And this has been predicted to occur theoretically as well. Why is this important? This is important because if you are able to use an electric field to manipulate the energy cost of putting electrons in orbitals, actually gives you an additional tuning knob for the induced phase transitions. And one thing that we are going after is about finding traces of this behavior in the dispersion of spin fluctuations in these materials. So spin fluctuations are essentially waves of spins in materials, and the energy of these spin waves is determined by the kinetic energy of the electrons and by the Coulomb repulsion. And if you modify the Coulomb repulsion, you can expect actually to change the energy cost of flipping a spin as well in materials. And this is really important for superconductors, for magnets, for quantum spin liquids. And in particular, we are interested in inducing spin liquid phases with light, and also in inducing alternative forms of superconductivity, such as the so-called Ida pairing condensation. That is a phase that has been postulated to exist in the 90s, but has never been found so far at equilibrium. But nevertheless, it's a rigorous state for the Hubbard Hamiltonian. It might be not the ground state. So you could obtain, as an example, a superconducting state in an excited form with particular correlation functions. So this is a bit a small overview of what you can actually do with X-rays, with ultrafast X-rays. This is the research we do. Before closing, I just wanted to say that in these talks, it's always the professor that talks, but actually the real heroes of the story are the people that have been working in my group. In particular, Denitsa Baikusheva is a postdoc with us since 1 year, and she has been doing phenomenal work with this experiment and in building the entire lab, essentially. Then Sophia Tenusen and Preston have been also doing measurements with us for this project. And Yao Wang at Clemson did really, and I think millions of core hours of calculations for us for this project, plus people at Pohang, UIUC, and BNL. And with this, I'm happy to answer to any other questions you might have.
Well, it's great. Thank you very much. It's fantastic you can get that. Or it's pretty difficult to do. Questions?
Yeah, I have one. So with the copper Hubbard U-band shift,
Yes.
it was almost like twice as much as the oxygen. Is that just because of the higher energy photon, or?
No, it's a bit different. It's so in this case, what we believe is the difference is that there is a different interactions with the core hole. And this is actually always the same band that is moving. So this is always a band. So there is a piece that I didn't tell you. These orbitals hybridize a bit. And since they hybridize a bit, you can see the copper states also at the oxygen edge. So you can see traces of the copper resonance also in the oxygen edge. But this is the same peak as this. The shift is different because there is a different interaction with the core hole. Because you are kicking one electron from the core into the valence band, and you left the core hole behind. And this forms like an excitonic state with the valence state.
Okay, I see. Great, thank you.
Welcome. Any other questions? Don't be shy.
I have a really simple question. So I think I understand why we care about the peaks shifting, but you said that we don't really care about the peaks broadening. And if the peak center stays at the same place, and I was wondering why that was.
Yes, because the peak broadening is really difficult to interpret in the sense that the peak broadening is contributed by multiple things. One thing that contributes to the peak broadening is the core hole lifetime. It's essentially like a resolution function in time. If you have that the core hole lifetime is really, really short, like a few femtoseconds, this will introduce a broadening. Plus, you might have additional broadening because you are coupling these states with phonons, and this will give rise to the formation of multiplets. But they don't really give you that much information, as a shift of the peak, because the shift of the peak gives you really the centroid of the energy of the band. That is the quantity that you're really interested into.
I see, okay.
Any other questions?
I also have one regarding the undulator of the free electron laser.
Yes.
I was wondering, like, what's the spacing of those magnets, and like whether changing the spacing has like a large effect on your X-ray pulse.
So yes, so changing the spacing is actually the way you tune the energy of the X-ray. So it has definitely a big effect. I have to remember, so I can tell you that the spacing between these magnets is of the order of centimeters. And I have to remember exactly, off of the top of my head right now, I don't remember exactly how many centimeters for a given energy, but I can look it up for you. But it should be as an example in any of these papers. So as an example, there is the first LCLS paper that is a Nature Photonics by Emma and other 50 people about the first lasing of the LCLS. And you should actually have details about the spacing of the undulator as well. But we are talking about centimeters here.
Okay, thank you.
Any other questions?
Last chance?
I don't want to cold people.
Okay, well, thank you very much. Really, I'm impressed. I think it's really not easy to do this, and then to be able to get kind of a sensitivity and resolution. But thank you very much. Thank
you very much, everyone. And Christina, you mentioned at the very beginning that you were curious about the physics that we do with respect to 15C. So does it answer your satisfy your curiosity?
This was amazing. Thank you, Professor.
Thank you.
Okay,
Thank you everyone for attending.
Yeah. I'll stop recording right now. Thanks again.